Welcome to this video on the fundamental limitations of probing quantum systems. Today, we'll explore why classical electromagnetic probes like light and electrons face fundamental roadblocks when we try to observe quarks, gluons, and other quantum constituents of matter. We'll focus on two key questions. First, could a quantum horizon hide mass at very small scales? And second, why can't voltage-driven probes directly liberate quarks and gluons from their confinement? Let's start by examining the fundamental quantum mechanical limits on observation. First, we have wave-particle duality. This principle tells us that any photon or electron we use as a probe will perturb the target as much as it images it. The act of observing changes what we're trying to observe. Second, Heisenberg's uncertainty principle states that delta x times delta p is greater than or equal to h bar divided by 2. This forces a fundamental trade-off between position and momentum precision. The more precisely we know where something is, the less precisely we can know how fast it's moving. Third, there's the observer effect. Measurement collapses quantum superpositions, altering the very state we wish to record. This isn't just a technical limitation. It's built into the mathematics of quantum mechanics. Finally, we have diffraction limits. The wavelength of our probing particle sets a hard floor on the features we can resolve. For optical microscopy, this limit is around 200 nanometers. Electron microscopy can reach subnanometer resolution, but we need even smaller wavelengths to observe quarks. Moving on to horizons in quantum physics. In classical physics, we're familiar with horizons like black hole event horizons and cosmological particle horizons. These represent boundaries beyond which information cannot reach an observer. But what about quantum analogs? Several speculative models exist. First, there's horizon quantum mechanics, which suggests probabilistic horizons for tiny masses. Unlike classical black holes, quantum-scale objects might have fuzzy, probabilistic horizons. Second, we have refractive index horizons in metamaterials. These are laboratory analogs where certain optical materials can mimic horizon-like effects for light. Third, Rindler horizons appear for accelerated observers. An observer accelerating in flat spacetime experiences an event horizon. Information from certain regions can never reach them. Finally, decoherence-induced information horizons occur when quantum systems interact with their environment. Information becomes effectively inaccessible due to entanglement with countless environmental degrees of freedom. Now, let's explore how quantum horizons might relate to mass obscuration. Einstein's famous equation, E equals mc squared, tells us that mass and energy are equivalent. At small scales, this equivalence blurs the distinction between mass and energy. An important insight: most of the mass of hadrons, like protons and neutrons, comes from QCD binding energy, not from the bare masses of quarks. The strong force between quarks creates most of the mass we observe. The quantum no-hiding theorem provides a crucial constraint here. It states that information, including mass-energy distribution, can never be truly destroyed. It can only be encoded elsewhere, such as in the entangled environment. This means true mass-hiding horizons remain highly speculative. While quantum effects may obscure direct observation, there's no established mechanism for completely hiding mass energy from all possible measurements. Let's now examine the temporal constraints on quark and gluon emission. The strong force operates on extremely short timescales, approximately 10 to the minus 23 seconds. In contrast, electromagnetic interactions operate on timescales greater than 10 to the minus 21 seconds. This timing mismatch is crucial. Typical voltage-driven probes simply can't overcome QCD confinement because they operate too slowly. By the time an electromagnetic force could pull a quark away, the strong force has already generated a new quark-antiquark pair to maintain confinement. The only condition where quarks and gluons can exist freely is in a quark-gluon plasma, or QGP. This state of matter requires temperatures above approximately 150 MeV, or about 1.7 trillion Kelvin. We can only achieve these extreme conditions through ultra-relativistic heavy-ion collisions, such as those at the Large Hadron Collider. Under these conditions, QCD bonds temporarily break, allowing quarks and gluons to move quasi-freely before rapidly recombining into hadrons. Despite these limitations, we're not completely blind to quark-gluon dynamics. Electromagnetic radiation provides valuable probes. Photons and leptons are particularly useful. because they escape the QGP undisturbed. They serve as excellent thermometers of the temperature and flow of the quark-gluon plasma. High-energy scattering processes, similar to Compton and Rayleigh scattering, can reveal momentum distributions of quarks and gluon field fluctuations. However, these require very short wavelength probes, less than about 0.01 femtometers. This table summarizes the wavelengths and energies of various probes and the scales they can resolve. As you can see, to probe quark structure, we need extremely high-energy particles, well beyond what conventional voltage methods can achieve. To conclude, let's summarize what we've learned and look at future directions. We've seen that fundamental quantum limits, uncertainty, disturbance, and diffraction severely restrict classical imaging at subfemtometer scales. Information horizons created by entanglement and decoherence further complicate our ability to directly observe quantum systems. Free quark and gluon emission requires extreme conditions found only in quark-gluon plasma, which demands temperatures far beyond what conventional voltage methods can achieve. Looking to the future, next-generation colliders like the Future Circular Collider and the Circular Electron-Positron Collider may create hotter, longer-lived quark-gluon plasmas for more detailed studies. Quantum sensors using entangled probes and squeeze states might push below current shot noise limits, offering new ways to extract information. Tabletop metamaterials could allow us to test refractive index horizons in laboratory settings, providing insights into quantum horizon physics. The fundamental constraints we've discussed aren't just technical limitations. They reflect the deep structure of quantum reality. While we may never see quarks and gluons in the classical sense, our evolving theoretical understanding and sophisticated experimental techniques continue to reveal their properties and behaviors.